Greetings, folks. You're going to be doing a lot of derivations in this class. Physics tends to be that way. There's a formatting approach that's quite useful. It's good for labs. It's also good for homework. This little video is designed to give you a shot at seeing what that formatting approach is. The problem we're going to deal with is an Atwood machine. Atwood machine consists of a pulley that's hung from the ceiling. String is looped over the pulley. Unequal mass is attached to either side. When you release the system, the masses accelerate. The question is to derive an expression for the acceleration of the system. This is a Newton's second law problem. I'm not going to do the whole problem, but I do want to show you the format as though you were starting the problem. So the first thing you would do is to write out a blurb. So a blurb effectively identifies what you're about to do. So if this was a lab and question number 3 said derive the acceleration for the system, you would write down 3 and then you would write down derive acceleration of system. That blurb lets you know exactly what it is that you're about to do. It would also let anybody who happens to be grading the lab know what it is that you're about to do. In the Newton's second law approach, the first thing that you normally do is to draw a free body diagram for the forces on at least one of the bodies in the system. So once again, you would blurb. You would write F, B, D for free body diagram on, I'm going to choose M1 as the body that I'm going to do the free body diagram for. Having done that, I would then proceed to draw the free body diagram. So there's my body. There is the tension force up, and I could call that F sub T, or I could call it just T. For simplicity's sake, I'm just going to call it T. I've actually kind of jammed things up here a little bit. You really want to kind of spread out on these things. In any case, you also are going to end up with a force down of gravity. Gravity is characterized by an mg. So in this case, I'm going to have to subscript the m because there are 2 of them. And I've just done my free body diagram. All the forces happen to be in the y direction. Once I have this, the next thing you want to do is to sum up the forces in the y direction. It turns out Newton's second law says that if you sum the forces in a particular direction, that will equal the mass times the acceleration in that direction. So once again, you need a blurb. And the blurb in this case is in the form, the sum of the forces in the y direction on M1. And then I'm going to put a colon and I'm going to underline it. And that's basically a blurb. I'm going to then drop down, indent in, because what I'm about to do comes under the context of this blurb. And I'm going to start the summation. So I've got a force up, and I'm going to put it in right there. And because it's up, I'm making up positive, so it's a positive force. I put it in as positive. Gravity is in the negative direction, so I'm going to put minus m1g. And that's the sum of the forces in the y direction. And according to Newton's second law, that will equal the mass of that body times the acceleration of that body. So there is my Newton's second law expression. Now, let us say that I decide that I want to solve for the tension. I would not drop right straight down. I would drop down and indent in. And in fact, I would actually put an implies sign because what I'm about to do is implied by this relationship. And I would do my algebra. So I'd have T is equal to M1G plus M1A. Notice I'm doing everything algebraically. Even though I had numbers in the original problem, M1 was 0.5 kilograms, you always want to do your derivations using algebraic symbols. So in the actual problem, you have 2 unknowns here. You don't know A, you don't know T. You need a second relationship. And you'd get that by doing a similar kind of a thing with the second mass. In this particular problem, though, simply because I want you to be able to see the format, I'm going to assume that you've been given the acceleration, and I'm going to assume that all you really want is the tension. So I'm going to go ahead and put the numbers in here. And so I would drop right straight down. I would not go over here and extend more information along this line. You want one equation per line. So I drop down, and underneath, right underneath the equal sign, I would start putting the information in. So I have 0.5 kilograms for a mass. I have 9.8 meters per second for the acceleration of gravity, g, plus 0.5 kilograms for the mass. I did the problem beforehand. It turns out the acceleration of this system is going to be 1.63 meters per second. And if you do the math, once you have these numbers down, you come up with a force of 5.72 newtons. And in fact, if you were looking for that tension, you would actually box that result. So once again, looking at the format, this is what I call an outline style. You will notice that you have dropped down and indented in because this belongs to this. You have dropped down and you've indented in because this is a consequence of this. I wouldn't put this right straight underneath. This makes it very easy to read. You only put one bit of information per line. You put numbers in at the end. So again, if we were trying to do this problem to completion, you would not do this line at all. You would simply go to the second mass and do this process for the second mass. You'd solve for the acceleration expression, and once you had that in algebraic form, then you would put the numbers in. But once you got to the point where you put numbers in, then you would do the math, you'd come up with a final expression, and you would box it. This is the format that you ought to be using for your derivations. Anyway, that's it. Have a nice day.